Tonight, we are going to take a closer look at Jupiter. Not the version most of us carry in our heads, not the giant planet in the outer solar system, far away and largely irrelevant to anything happening here. We are going to look at what Jupiter actually is, what it actually does, and why the word terrifying is not an exaggeration. Jupiter has been in our sky for all of recorded history. Every civilization that looked up saw it. Most thought it was a star, a bright one, a wandering one, but still just a point of light in a familiar sky. Here is what most people do not realize. Jupiter is not simply the largest planet. It is so massive that the solar system's structure was written around it. Its gravity has torn moons apart, created oceans where there should be none, swallowed comets whole, and may have played a direct role in making Earth the kind of planet it became. By the end of tonight, you are going to understand why Jupiter's size is not just a record, why its influence reaches far beyond anything its image suggests, and why the word terrifying is the most accurate one available. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. There is an image of Jupiter that most people carry without knowing they carry it. It is a photograph, or perhaps the memory of a photograph. A planet seen from some distance, its surface wrapped in horizontal bands of orange and cream and brown, the colours soft enough to feel almost painted. Near the southern equator, a dark reddish oval sits in the cloud layer. A great red spot. You have probably seen it dozens of times in books, on posters, in school presentations, printed large on the walls of science classrooms or displayed on the screens of planetarium shows. It is one of the most reproduced planetary images in the history of planetary science. The image has become so familiar that it carries the feeling of completeness. This is Jupiter. Banded, stormy, large, the image tells you what the planet is, in the same way that a photograph of a mountain tells you what a mountain is. You see it, you recognize it, you file it. That image is accurate. The colors are real, the storm is real, the banding is real. But the image does something that all images of distant objects do. It simplifies. It takes an object hundreds of millions of kilometers away and reduces it to something the eye can hold, something the brain can file neatly into a category. Large outer planet, impressive, noted, next. The category is not wrong. The filing is not irrational. The image gives you everything that light reflecting off Jupiter's cloud tops and travelling across the inner solar system to a camera can give you. That is genuinely what it looks like from this distance. What the image cannot give you is everything else. The problem with that filing system is what it leaves out. When Galileo turned his telescope toward Jupiter in the winter of 1609, he saw something no one had expected. 4 small points of light near the planet, arranged in a line, changing position from night to night. He tracked them over weeks and slowly understood what he was looking at. These were moons, objects orbiting something other than Earth. It was one of the first direct visual arguments that Earth was not the fixed centre around which everything moved. Galileo saw the moons. He was not able to see what was producing them. It took another 350 years and a spacecraft crossing hundreds of millions of kilometres to get the first close look. Voyager 1 flew past Jupiter in March of 1979, sending back photographs of a world that the centuries of Earth-based observation had only partially described. The atmospheric banding was there as expected. The great red spot was there as expected. But then Voyager showed things that no one had seen before. The turbulent, rope-like cloud structures at the boundaries between atmospheric bands. the intricate spiraling patterns at the edges of the Great Red Spot, the volcanic plumes rising off Io, the strange streaked surface of Europa. The planet behind the image was more complex than the image had suggested, and in a sense, most people today are in a similar position to where humanity was before Voyager. We know the moons exist, we know the planet is large, we know the storm is famous. But the image carried in the cultural memory, the banded disk with the red spot, conveys almost none of what the planet actually does, what its interior contains, what it has done to the worlds around it, and what its presence has meant for the shape of the solar system over billions of years. Standing outside on a clear night and looking at Jupiter with your naked eye, you see a bright, steady, slightly yellowish point of light. It does not twinkle the way stars do, because it is close enough that it has a visible disk, even if that disk is too small for the human eye to resolve. It is simply bright, calm, fixed in one place relative to the stars around it, though it moves slowly over weeks and months as it orbits the Sun. That stillness is an illusion created by distance. What you are actually looking at from that distance is a planet with an atmosphere where winds run at hundreds of kilometers per hour and have been running continuously for as long as the planet has existed. A planet with no solid surface to stand on, no ground beneath the clouds, just increasing pressure as you descend until the physics of ordinary matter stops applying. A planet whose interior contains hydrogen under conditions so extreme that the hydrogen stops behaving like a gas and begins conducting electricity like a metal. A planet that generates a magnetic field so large that if it were visible from Earth, it would appear wider than the full moon in the night sky. And that is before you get to what it does to the worlds around it. The 4 moons Galileo saw are each a world in their own right. One of them is the most volcanically active body in the solar system, continuously torn apart and rebuilt by Jupiter's gravity. Another has a liquid water ocean, larger than all of Earth's oceans combined, hidden beneath a shell of ice, in a place where the sun provides almost no warmth. A third is larger than the planet Mercury and has its own internally generated magnetic field. A fourth sits on the outer edge of Jupiter's gravitational family, geologically quiet, its surface ancient and unchanged. A record of what these moons might have been if Jupiter had not reached into their interiors and started pulling. None of this is visible in the image. None of it is suggested by the calm banded disk that greets you through a telescope. That is the first thing you need to understand about Jupiter. The image is real. The planet behind the image is something else entirely. Size is the word most people reach for when they try to describe Jupiter. And they are not wrong. Jupiter is large. Unambiguously, record-settingly large. But the word large is a category, not a description. It tells you where to file the information. It does not tell you what the information means. So let us be more specific about what Jupiter's size actually is, and then, more importantly, what that size does. If you took every other planet in the solar system and placed them all inside Jupiter, they would fit. Not crowded, not barely. You would fill Jupiter with all the other planets and still have room remaining. Jupiter's volume is more than 1,000 times the volume of Earth. More than 1,000 Earths could be nested inside it before it was full. That is volume. Volume is impressive. But volume is not the thing that changes how a solar system works. What changes a solar system is mass. Jupiter contains more mass than every other planet in the solar system combined. Then double that total. Jupiter is still heavier. Its mass is roughly 318 times the mass of Earth. When astronomers calculate the center of mass of the solar system, the point around which the Sun itself wobbles slightly as the planets orbit, that point is influenced more by Jupiter than by any other planet. The Sun does not sit perfectly still at the centre of the solar system. It moves in a slow, small ellipse, pulled by the gravitational tug of the combined planetary mass. Jupiter is the dominant force in that pull. Planetary scientists use the term barycenter for this centre of mass. Earth and the Moon have their own barycenter, a point slightly below Earth's surface, around which the two bodies technically orbit each other. The Sun and Jupiter have a barycenter that sometimes falls just outside the Sun's surface, meaning the Sun itself literally orbits a point in space pulled outward by Jupiter's mass. Every other planet in the solar system combined does not exert enough gravitational pull to move the Sun's barycenter outside the Sun's body. Jupiter does it alone. That single fact carries the entire argument of this script inside it. One planet, orbiting the Sun at a distance 5 times greater than Earth, is massive enough to make the Sun itself move. Not metaphorically. Not in some indirect sense. The Sun traces a small ellipse, a real physical displacement, because Jupiter is there. That is the gravity involved. That is the mass involved. That is what all the consequences discussed in this script flow from. This is not a technical detail with no real-world consequence. It is a physical reality that has been shaping the solar system since Jupiter formed. Mass creates gravity. Gravity at Jupiter's scale does not simply attract objects, it reorganizes them. In the early solar system, when the planets were still forming from the disk of gas and dust orbiting the young Sun, Jupiter was among the first large objects to form. The leading model of planet formation suggests that the cores of giant planets form relatively quickly from solid material in the outer solar system, then sweep up gas from the surrounding disk before the disk disperses. Jupiter formed while the disk still had gas to offer. It became the solar system's first massive world. And once Jupiter was large enough, its gravity began imprinting itself on everything nearby. The asteroid belt, the sparse region of rocky bodies between Mars and Jupiter, exists in its current state because Jupiter would not allow it to be anything else. Material that might have clumped together into a planet was continuously stirred by Jupiter's orbital resonances, precise gravitational nudges arriving at mathematically regular intervals, preventing any object from settling into a stable enough orbit to merge with its neighbours and grow larger. The belt is not an incomplete planet. It is a region where Jupiter did not allow a planet to form. Comets from the outer solar system, long elliptical travellers from the cold dark beyond Neptune, are regularly intercepted by Jupiter's gravity as they fall inward toward the Sun. Some are deflected outward, some are captured, some are redirected inward. Jupiter's gravitational reach, the sphere of space where its gravity dominates over the Sun's, extends across hundreds of millions of kilometres. Objects entering that sphere do not simply continue on their original paths. Jupiter even influences the Sun, not dramatically, but measurably. The centre of mass of the solar system, the true gravitational centre around which everything orbits, shifts depending on where Jupiter is in its orbit. When Jupiter is on one side of the Sun, the centre of mass shifts slightly in that direction, and the Sun orbits that point in a small wobble. The Sun moves because Jupiter is there. This wobble is not merely a theoretical curiosity. It is the same effect that astronomers use to detect planets around other stars. When a distant star wobbles slightly in its position, repeating the movement with a regular period, astronomers infer the presence of a large orbiting body pulling the star from side to side. The technique is called radial velocity detection, and it has been used to discover hundreds of exoplanets orbiting other stars. Our own sun's wobble, detectable by a distant enough observer, would announce Jupiter's presence to any astronomer watching from another solar system. Jupiter is literally visible at interstellar distances through the effect of its gravity on the Sun. The technique that could reveal Jupiter to distant observers is the same technique that has revealed Jupiter-like planets around other stars, and, in doing so, has shown that Jupiter-sized planets in Jupiter-like orbits are not the rule. Many planetary systems discovered so far have no Jupiter analogue. Others have Jupiter-sized planets in far smaller orbits, closer to their host stars than Mercury is to the Sun, what astronomers call hot Jupiters. The architecture of planetary systems varies enormously. Whether solar systems with no outer giant planet tend to produce different inner planet conditions than solar systems with a Jupiter-like outer planet is an active area of research. The question of whether Jupiter's presence has been ultimately beneficial or hazardous for the development of life on Earth, if it can ever be answered, is also a question about whether solar systems need a Jupiter to be potentially habitable. That is what size means when size becomes mass and mass becomes gravity. When you look at Jupiter as a bright point in the night sky, you are looking at the planet that has most actively shaped the solar system you live in. Not the Sun, which holds everything in orbit through sheer dominance, but Jupiter, which has spent billions of years quietly reorganizing everything in its reach. The record for largest planet is the least interesting thing about it. Imagine you are falling into Jupiter, not crashing into a surface, falling, drifting downward into the upper atmosphere, slowly, the way a parachutist descends through cloud cover. You pass through the top of the cloud deck. The sky above you slowly transitions from the black of space to something more complex, amber and white and yellow. The undersides of cloud layers lit from above by diffuse light travelling hundreds of millions of kilometres from the Sun. You keep falling. The pressure increases. Not dramatically at first. The upper atmosphere of Jupiter is thin enough that the sensation might feel, in some ways, not entirely unlike the upper layers of Earth's own atmosphere. Cold, thin, the clouds around you are made of ammonia crystals, the same compound you might find in industrial cleaning products, frozen into ice particles at these high, cold altitudes. Below the ammonia clouds, you descend through a layer of ammonium hydrosulfide clouds. This compound, a combination of ammonia and hydrogen sulfide, is responsible for much of the brownish-orange colouring visible in Jupiter's darker bands. The chemistry is changing around you. The pressure is increasing. You are moving deeper. Below that, water vapour and water ice clouds appear. This is a region scientists believe exists inside Jupiter's atmosphere, but have only inferred indirectly, because it sits below the level that telescopes can observe from outside. The specific altitude of the water cloud layer and the amount of water in Jupiter's atmosphere have been subjects of significant scientific debate. The Galileo probe provided direct measurements from one entry point and found less water than expected. But that entry point happened to be one of Jupiter's dry hotspots, an unusual region that was not representative of the global atmosphere. Juno's microwave radiometer instrument has since measured water content across a wider range of latitudes and has provided evidence that Jupiter's atmosphere does contain substantial water, though the global distribution is uneven. The Galileo probe measured some of the conditions in this region before the pressure became too great. You keep falling. The temperature begins to rise, not because the Sun is warming you. You are moving away from the Sun. The heat is coming from below, from Jupiter's interior, which is still slowly releasing gravitational energy from its formation billions of years ago. When Jupiter formed, enormous quantities of gas collapsed inward under their own gravity, converting the energy of that infall into heat, The planet has been radiating that heat outward ever since. Jupiter emits roughly 1.5 to 2 times more energy than it receives from the Sun. The planet is a warm object in the outer solar system, not because it is close to a star, but because it is still cooling down from the violence of being born. That internal heat rises as convection, warm gas moving upward, cooler gas sinking down, a continuous circulation that feeds the atmospheric systems above it. You keep falling. The pressure around you is now tens of times Earth's atmospheric pressure, then hundreds of times. The atmosphere has thickened from gas into something with more resistance, more density, something that no longer quite behaves the way gases behave in any human scale experience. The distinction between gas and liquid is beginning to blur. Jupiter's atmosphere does not have a sharp boundary between gas above and liquid below. It transitions gradually, the material becoming denser and denser as you descend, until the concept of a gas phase no longer applies. And still, no surface. There is no moment where your feet find something solid. There is no transition from air to ground. There is only the slow, relentless increase in density and pressure as you continue downward through a planet that simply has no floor. In 1995, a small spacecraft called the Galileo atmospheric probe entered Jupiter's atmosphere and descended for approximately 57 minutes before the pressure and temperature destroyed it. The probe was roughly the size of a large bathtub and contained scientific instruments measuring temperature, pressure, chemical composition, and wind speed. It descended through roughly 160 kilometers of atmosphere, transmitting data back to the Galileo orbiter above it, until the increasing pressure and heat overwhelmed its structure and it stopped transmitting. It never found a surface. It simply fell until the planet absorbed it. 160 kilometers sounds like a significant distance. It is not, relative to Jupiter. The full radius of Jupiter is roughly 70,000 kilometers from cloud tops to center. The Galileo probe made it through slightly more than 0.2% of the planet's depth before it was destroyed. What lies below that point, what the transition from thick atmosphere to whatever the interior becomes, has never been directly measured. It has only been modelled. The models suggest that below the cloud layers the gas becomes increasingly dense. The boundary between gas phase and liquid phase gradually disappears as pressure continues to increase. The material becomes a kind of supercritical fluid, neither quite gas nor quite liquid in any ordinary sense. Below that, conditions change again as hydrogen is compressed beyond anything the upper atmosphere experiences. The atmosphere is not the bottom of Jupiter. It is not even close. It is the outermost visible skin of a planet that extends downward through physics that nothing built on Earth could survive. The absence of a surface is not a deficiency. It is a consequence of how much mass is present. Enough mass, held together by gravity, and the material arranges itself into a gradient of increasing density with no solid floor necessary. Earth has a surface because Earth is small enough and cool enough for its material to solidify. Jupiter is too large and too hot for that, and it never needed to be. At some depth below Jupiter's cloud tops, something happens to hydrogen that has no counterpart in everyday experience. Hydrogen is the simplest element in the universe. One proton, one electron. The lightest element, it is what stars burn for fuel. It is what the early universe consisted of almost entirely, before any heavier elements were made in stellar interiors. In ordinary conditions, two hydrogen atoms bond together into a molecule and exist as a colourless, odourless gas. It is the lightest gas, the easiest to lift. The first element on the periodic table, under extreme enough pressure, hydrogen stops being any of those things. It becomes something that for most of human history was considered impossible. To understand what happens inside Jupiter, it helps to think briefly about what makes a metal a metal. Metals conduct electricity because their electrons are not tightly bound to individual atoms. In a piece of copper wire, for example, electrons move relatively freely through the material, drifting from atom to atom in response to an applied voltage. This is why copper carries electrical current so efficiently. The electrons are in a sense shared across the entire metal. They belong to the material as a whole rather than to individual atoms. Now imagine taking hydrogen gas and compressing it with extraordinary force. Not a little. Enormously. Compress it until the individual hydrogen molecules are forced so close together that the normal separation between atoms simply collapses. At those pressures, somewhere in the range of millions of times greater than Earth's atmospheric pressure at sea level, the electrons that normally belong to individual hydrogen atoms are squeezed out of their atomic associations. They become free to move through the material. They form a shared conducting sea. The hydrogen has not changed its nuclear composition. It is still hydrogen. But it now conducts electricity. It now behaves for all physical purposes that matter, like a liquid metal. This state is called metallic hydrogen. It does not exist naturally anywhere on Earth. The pressures required are far beyond anything Earth's interior generates, or anything human technology has created in sustained conditions. Brief flashes of metallic hydrogen have been created in laboratory experiments using extreme compression techniques, and those experiments have confirmed that hydrogen does indeed transition toward a conducting state at very high pressures. The physics is not speculative, but the sustained oceanic scale of metallic hydrogen that exists inside Jupiter is something no laboratory has produced and no direct measurement has ever reached. Laboratory experiments have attempted to create metallic hydrogen under controlled conditions, with varying degrees of success and controversy. In 2017, a team at Harvard University reported that they had compressed hydrogen in a diamond anvil cell, a device that squeezes material between two diamonds to achieve extreme pressures. To pressures estimated at roughly 4.95 million times Earth's atmospheric pressure, and observed what they interpreted as a transition to a metallic state. The report was controversial, and the sample was lost when the apparatus failed before independent verification could be completed. The experiment has not been definitively replicated. The physics underlying metallic hydrogen is not in dispute, but creating and maintaining a sample long enough to study it is an extreme experimental challenge. Jupiter does not have this problem. Jupiter simply has more mass than any laboratory and more time than any experiment. What scientists are confident about is what a vast spinning body of conducting fluid does. When electrically conducting material moves, it can generate a magnetic field. This is the principle behind every electrical generator ever built. A coil of copper wire rotating inside a magnetic field generates current. Earth's liquid iron outer core, moving in slow convection patterns, generates Earth's magnetic field by the same principle. The movement of conducting material creates and sustains a magnetic field. Inside Jupiter, deep below the cloud tops, the metallic hydrogen is not sitting still. Jupiter rotates on its axis roughly once every 10 hours, the fastest rotation of any planet in the solar system. That rapid rotation, combined with a convection driven by internal heat, moves the metallic hydrogen in complex patterns. And that moving conducting fluid generates a magnetic field. The precise depth at which metallic hydrogen begins in Jupiter's interior, and the precise depth at which it transitions to whatever lies even further down, near the planet's core, are not precisely known. Models suggest the metallic hydrogen region may begin somewhere around 20,000 to 30,000 kilometers below the cloud tops, roughly a third of the way to Jupiter's center, and may extend for another 30 to 40,000 kilometers inward. At the center of Jupiter, current models suggest there may be a core of heavier elements, rock and metal, though whether this core is solid, liquid, or in some transitional state at those conditions is uncertain. Some models suggest the core may be diffuse, partially dissolved into the surrounding metallic hydrogen rather than existing as a distinct compact object. Juno has been measuring Jupiter's gravitational field in unprecedented detail, and those measurements are helping to constrain what the interior structure looks like. The results so far suggest the core region may extend further outward than classic models assumed, a dilute core rather than a compact one. But the measurements are still being interpreted, and the precise structure of Jupiter's interior remains one of the important open questions in planetary science. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's. That number needs translation to mean anything. Here is one way to understand it. Jupiter's magnetic field creates a region of space called the magnetosphere, the zone where Jupiter's field dominates over the solar wind's influence. In the direction of the Sun, Jupiter's magnetosphere extends outward for roughly 600 to 700 million kilometers. On the opposite side, away from the Sun, it stretches even further, creating a magnetic tail that extends past the orbit of Saturn. If Jupiter's magnetosphere were somehow visible to the naked eye from Earth, it would appear in the night sky as a structure larger than the full moon. The Sun itself would appear smaller compared to the extent of Jupiter's magnetic influence, then Jupiter's magnetosphere would appear from this distance. The source of that field is not iron, the way Earth's field is. It is hydrogen, the lightest element, pressed by the weight of a planet into a form that conducts electricity like a metal and spins like a vast generator. That generator has been running for billions of years. And what it produces, that enormous magnetic field, does not sit quietly around Jupiter. It reaches into the space around the planet, traps particles, accelerates them, and creates a radiation environment that makes Jupiter's vicinity one of the most hostile places in the solar system. There is a storm on Jupiter that has been running since before the United States existed, possibly much longer. The Great Red Spot is not a storm in the way that hurricanes or cyclones are storms on Earth. On Earth, a storm is an event. It forms when conditions align, it intensifies, it travels, it encounters land or cooler water or upper-level wind shear, and it weakens and ends. The most persistent tropical cyclones on Earth might maintain themselves for a few weeks. The most powerful and long-lived hurricanes in recorded history have lasted a month, perhaps a little more, before they finally dissipated. The Great Red Spot has been continuously observed since at least the mid-1800s. Some historical records suggest a large storm feature in Jupiter's southern hemisphere may have been observed as early as the 1660s by the Italian-French astronomer Giovanni Cassini. Though whether the oval feature Cassini described and the storm visible in modern telescopes are the same continuously running atmospheric feature is a question that careful historians of astronomy have debated for decades. The historical record is not detailed enough to confirm continuity over more than 3 centuries. What is certain is this: for as long as humans have been watching Jupiter with instruments capable of resolving detail on its surface, the Great Red Spot has been there. It was running when Abraham Lincoln was alive. It was running during the construction of the transcontinental railroads. It was running when the Napoleonic Wars reshaped Europe. It was there when the first steam engines were being tested in the mills of northern England. It was there when Mozart was composing in Vienna. If the historical records are right and the storm dates to the 1660s, it was running when Isaac Newton was a young man in Cambridge, working out the laws of gravity, the same mathematical laws that govern the atmospheric dynamics responsible, in part, for why the storm exists at all. Every human civilization that has built an optical telescope capable of resolving Jupiter's disk has seen the storm. It has been painted. It has been drawn in scientific papers. It has been photographed when photography became available. It has been captured by spacecraft cameras at close range. No other feature of any other planet has been under continuous observation for as long and from as many different vantage points and technologies as the Great Red Spot. To understand why the Great Red Spot persists where an Earth storm cannot, you need to understand what stops a storm on Earth. On Earth, storms lose energy when they make landfall. The friction of the surface disrupts the atmospheric circulation. Storms also weaken when they move over cooler water, losing the warm, moist air that feeds them. The geography of Earth, the continents, the varying ocean temperatures, the mountain ranges that redirect airflow, is in a sense a storm dissipation system. Earth's surface works continuously to pull storms apart. Jupiter has none of that. There is no land for a storm to encounter. There is no coastline, no mountain range, no patch of cooler ocean water. The atmosphere of Jupiter extends downward through tens of thousands of kilometers of increasing density with no surface to interact with. A sufficiently large atmospheric vortex on Jupiter, a rotating system that has grown large enough to become self-sustaining, can persist indefinitely because there is nothing available to interrupt it. The same energy input that feeds the storm, internal heat rising from below and solar energy arriving from above, continues operating without any mechanism available to redirect it or cut it off. The Great Red Spot is an anticyclonic storm, a high-pressure rotating system in Jupiter's southern hemisphere. Its current size is roughly 10,000 to 13,000 kilometers across. At various points in the historical record, when telescopes began producing measurements detailed enough to track it, the storm was estimated to be significantly larger. Some measurements from the late 1800s and early 1900s suggested the storm was wide enough to hold 2 or 3 planets the size of Earth side by side. Even now, in its reduced form, it is still wider than Earth. One storm. One persistent location in the southern atmosphere. Rotating continuously for a minimum of 150 years of systematic observation, and possibly for 350 years or more if the historical observations track the same feature. The colours of the Great Red Spot have also changed over time. Early observations recorded it as a prominent red-brown oval. In more recent decades, it has often appeared a more muted orange or salmon colour. The chemistry responsible for the red coloration is not fully understood. One hypothesis is that ultraviolet light from the sun breaks down ammonia and acetylene compounds in the upper atmosphere of the storm, producing reddish chemical products. But the precise mechanism that determines the colour of the storm at any given time remains an area of ongoing research. The storm is also changing in size. Over the past century and a half of careful measurement, the Great Red Spot has been getting smaller. The rate of shrinkage has varied, with some periods of faster change and some of relative stability, but the long-term trend is clear. The storm that was once large enough to hold multiple Earths has been contracting. In the past few decades, some observations have noted that the storm has occasionally developed irregular shapes, flaking off smaller vortices at its edges, its normally elliptical outline becoming more circular and less stable looking. What is causing the shrinkage is not fully understood. One possibility is that the storm is simply interacting differently with the surrounding atmosphere as conditions change. observations have shown smaller vortices peeling away from the storm's edges, structures that researchers have informally called red blobs, and there is some evidence that these ejected vortices may carry away material and energy that was previously sustaining the main storm. Another possibility is that changes in Jupiter's overall atmospheric dynamics, shifts in the jet streams or in the thermal structure of the atmosphere at the latitudes where the storm sits, are altering the conditions that have historically fed it. Whether the Great Red Spot will eventually dissipate entirely, stabilize at a smaller size, or persist for centuries more in some altered form is a question the available data cannot yet resolve. Juno's ongoing observations have provided the most detailed view of the storm's three-dimensional structure, revealing that the storm's roots extend roughly 500 kilometers below the visible cloud tops, deeper than many atmospheric models had predicted. The storm is not a surface feature, it has depth. What is not in question is what it represents, a single atmospheric feature driven by Jupiter's internal heat and the absence of any surface friction that has been in continuous rotation for longer than most human institutions have existed. By the timescales that govern the weather systems of this planet, the Great Red Spot is not notable for being a storm. It is strange because it is a storm that never had a reason to stop, and it may be in the very slow process of finally finding one. The Great Red Spot is the most visible piece of Jupiter's weather, but it is not the most extreme. Look at any photograph of Jupiter taken from a distance. The horizontal banding, those alternating stripes of lighter and darker cloud material, looks almost orderly. The colours stack neatly, one band above another, the whole planet wrapped in parallel lines that give it an almost deliberate, organised appearance. That appearance is the surface expression of something deeply energetic happening underneath it. Those bands are not cloud formations in the way Earth's clouds form around a low-pressure system or a cold front. They are the visible tops of competing jet streams, powerful rivers of gas moving at high speed in alternating directions around the planet. Some of these streams flow eastward, some flow westward. They alternate with latitude, so that above one band the gas is flowing east, and above the next band the gas is flowing west, and the boundary between them is a zone of shear and turbulence. The lighter coloured zones in Jupiter's banding are regions of rising gas. The darker, more brownish belts are where gas is sinking. The colour difference between zones and belts comes from the chemistry at different altitudes and temperatures. Ammonia clouds at high altitudes tend to appear lighter. Lower, warmer regions where different chemical compounds are present appear darker. Where the jet streams meet, at the boundaries between the rising zones and the sinking belts, the atmosphere is not peaceful. Close-up images from the Voyager spacecraft, and later from the Juno mission's JunoCam instrument, show those boundary regions in detail, and what they reveal at high resolution is not orderly stripes at all. They are complex knots of cloud, folded structures, swirling filaments, what scientists call festoons, elaborate braided patterns where atmospheric material is being churned at the interface between two streams moving in different directions. The orderly banding is real, but it is the large-scale view. Close up, the boundaries are turbulent. The jet streams themselves move at speeds that have been measured by tracking cloud features and by direct instruments carried by the Galileo probe. In some of Jupiter's atmospheric bands, wind speeds reach roughly 500 to 600 kilometers per hour. In some regions, measurements have suggested even higher speeds in localized areas. For reference, the most powerful tornado ever recorded on Earth reached peak wind speeds of roughly 480 kilometers per hour, and it lasted for minutes, moving across a track of a few hundred kilometers before it dissipated. A tornado at that intensity is considered an extreme, rare, catastrophic event on Earth. Jupiter's jet streams are planetary in scale. They circle the full circumference of a planet more than 140,000 kilometers wide. They have been running since the planet formed. They are not events, they are the baseline condition of Jupiter's atmosphere. There is a physical reason they do not slow down. On Earth, the atmosphere is continuously dragged and redirected by terrain. Mountain ranges push airflow upward and redirect it horizontally. Oceans transfer heat to the air above them in patterns that change with season and geography. Coastlines interrupt circulation. The entire surface of Earth is an enormous friction machine that constantly works on the atmosphere above it, slowing it down, breaking up patterns, redirecting energy. Jupiter's atmosphere encounters nothing like this. Below the cloud deck, the gas simply becomes denser and denser until it transitions to a supercritical fluid and eventually to metallic hydrogen, and at no point in that downward progression does anything function like a surface. There is no terrain to push the wind sideways. There is no coast to interrupt a flow that has been building for billions of years. A wind pattern that starts moving on Jupiter has nothing in its path to slow it down. Jupiter also generates its own heat from below. That internal heat drives convection, warm gas rising, cooler gas falling, in columns and patterns that feed energy continuously into the atmospheric circulation from underneath. Combine the solar energy arriving from above and the internal heat rising from below, with no surface available to dissipate either, and the result is an atmospheric engine that has been running continuously since the solar system was young. The Juno mission, which has been making close passes of Jupiter since 2016, has provided the most detailed view of Jupiter's atmospheric structure ever obtained. Its microwave radiometer instrument can measure thermal emission from different depths below the cloud tops, effectively allowing scientists to see further into the atmosphere than any telescope or spacecraft had before. What those measurements revealed is that the jet streams are not shallow features confined to the visible cloud layer. They extend downward for roughly 3,000 kilometers below the cloud tops before tapering off. The organized band structure visible from Earth has roots that go far deeper into the atmosphere than the surface images suggest. 3,000 kilometers of organized atmospheric motion below the visible surface. The image shows the cloud tops. The jet streams continue for a depth greater than the diameter of Earth's moon. Juno also revealed something unexpected at Jupiter's poles. Images from previous spacecraft had shown Jupiter's polar regions, but not in detail. When Juno's camera captured the poles in high resolution, what it found were enormous cyclonic storm systems, polygonal arrangements of individual cyclones clustered together. A large central cyclone surrounded by a ring of smaller ones, the whole arrangement locked in a geometric pattern. The North Pole has a central cyclone surrounded by 8 others. The South Pole has a central cyclone surrounded by 5. These polar storm arrangements had not been predicted by atmospheric models. They are still being studied, and their long-term stability and the dynamics that maintain them in their polygonal arrangement are not fully understood. Jupiter's atmosphere is not just the bands visible from Earth. It is a system that continues to reveal unexpected structure at every scale at which it has been examined closely. The banding you see in the photographs is not decoration. It is the large-scale view of an atmospheric system that has been operating without interruption for roughly 4.5 billion years, the age of the solar system itself. And much of what drives it sits in depths and at polar latitudes that no instrument has yet fully characterized. Jupiter's magnetic field does not simply exist around the planet, it does something to the space it occupies. Any magnetic field traps charged particles, the electrons and protons that stream outward from the Sun as solar wind. Earth's magnetic field does this too, and the result is the Van Allen radiation belts. two donut-shaped regions of trapped high-energy particles encircling Earth at various altitudes above the surface. Astronauts and spacecraft avoid spending extended time in these regions because of the radiation exposure involved. The belts are real and they require planning to work around, but they are manageable. Earth's magnetic field creates radiation zones that spacecraft can navigate. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's. The radiation belts that result are not simply a scaled-up version of Earth's, they are a different category of environment. The particles trapped in Jupiter's radiation belts are accelerated to higher energies by the stronger field. They are present in greater concentrations, they occupy a much larger volume of space, and they are continuously replenished not only by the solar wind, but by an additional source that is unique to Jupiter's system. A source that will come up shortly, because it is connected directly to one of Jupiter's moons. Every spacecraft designed to operate in or near Jupiter's magnetosphere has had to account for the radiation environment in its engineering from the beginning of the design process. The Galileo spacecraft, which entered Jupiter's orbit in 1995 and spent roughly 8 years studying the planet and its moons, accumulated significant radiation damage over the course of its mission. It was not designed to be completely immune to the environment. It was designed to survive long enough to accomplish its science objectives while being carefully managed to minimize exposure. Its orbit was shaped to reduce time spent in the most intense radiation zones, but complete avoidance was never possible. The Juno spacecraft, which arrived at Jupiter in 2016 and has been conducting close polar orbits of the planet since then, carries a titanium radiation vault, a box of thick, hardened metal surrounding the spacecraft's most critical electronics, designed to reduce the radiation dose those components receive on each close pass. Even with that shielding, each perijove, each close approach to Jupiter along Juno's highly elliptical orbit, accumulates a measurable radiation dose. Engineers track that cumulative dose carefully, knowing the spacecraft has a finite tolerance before the damage becomes operationally significant. For a human being, without specialized radiation shielding, somewhere in the vicinity of Jupiter's inner moons, the radiation environment would be lethal within minutes, not dangerous over years, not something that would require monitoring and occasional medical treatment. Minutes, that is not a projection from theoretical models alone. It is a conclusion based on particle flux measurements taken by instruments on spacecraft that entered those regions and recorded what the environment actually contained. Jupiter's magnetic field does not behave the way Earth's magnetic field behaves. Earth's field is understood, broadly, as a protective feature. It deflects the solar wind, it creates the auroral displays at high latitudes, it provides the navigational reference that compasses have used for centuries. It is part of the system that allows Earth's atmosphere to persist without being stripped away by the solar wind. Jupiter's field does all of that for Jupiter. But at this scale, it also does something else. It takes the particles arriving from the solar wind, adds the material produced by volcanic activity on one of its own moons, accelerates all of it to high energies, concentrates it in the space around the planet, and creates a radiation environment that makes the space near Jupiter actively hostile in a way that has no equivalent in the inner solar system. The magnetic field is not a weapon in any intentional sense. It is simply physics operating at a scale that produces extreme outcomes. But the extreme outcome is real, and any object, any spacecraft, any hypothetical future human mission approaching Jupiter closely enough to enter the strongest regions of that field has to contend with an environment that will eventually destroy it. The particles in Jupiter's radiation belts are not simply solar wind protons and electrons. They include material from Jupiter's volcanic moon Io, sulfur and oxygen ions that have been stripped from Io's volcanic plumes and fed into the magnetosphere over billions of years. Jupiter's magnetic field accelerates these ions to energies that can penetrate metals. The synchrotron radiation that high-energy electrons produce as they spiral along Jupiter's magnetic field lines is intense enough to be detectable from Earth using radio telescopes. Jupiter is a source of radio emissions partly because of what its radiation belts are doing. That radio signature was actually one of the first pieces of evidence that Jupiter had a strong magnetic field. Detected by Earth-based radio telescopes in the 1950s, long before any spacecraft visited the planet. The radiation belts were announcing themselves across the solar system. The difficulty of working near Jupiter was built into its radio signature decades before any mission had to contend with it directly. Before exploring what Jupiter has done to the worlds inside its gravitational reach, it helps to understand the mechanism through which that reach operates on those moons. Jupiter's 4 largest moons are called the Galilean moons, after the astronomer who first recorded them in 1609. Their names are Io, Europa, Ganymede, and Callisto. They orbit at different distances from Jupiter, with Io the closest and Callisto the furthest out, and 3 of the 4, specifically Io, Europa, and Ganymede, are locked into a precise gravitational rhythm with each other that has enormous physical consequences for their interiors. For every 4 times Io completes an orbit of Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 1. This is not a coincidence, and it is not a stable but arbitrary arrangement that happened to come about by chance. It is a gravitational resonance, a state in which the regular gravitational interactions between the 3 moons have, over billions of years, synchronized their orbital periods into a precisely locked ratio. This relationship is called the Laplace resonance, after the French mathematician Pierre-Simon Laplace, who described its mathematics in the 18th century. From the outside, this sounds elegant. 3 worlds in a perfect mathematical relationship, moving around a large planet in coordinated orbits. The consequence for the moons themselves is less gentle. When moons are locked in resonance, they encounter each other gravitationally at the same relative positions in their orbits, repeatedly, with the same timing. These regular encounters prevent the moons from settling into perfectly circular orbits. Instead, their orbits are kept slightly elliptical, slightly stretched. On one side of their orbit they are closer to Jupiter, on the other side they are further away. That changing distance matters because of how gravity works. The near side of a moon, the side facing Jupiter, is closer to Jupiter's centre of mass than the far side. Jupiter's gravitational pull on the near side is therefore slightly stronger than its pull on the far side. This difference in gravitational force across the diameter of the moon is called tidal force. Earth's oceans rise and fall because of tidal forces from the moon pulling slightly more strongly on the ocean on Earth's near side than on the far side. When a moon's orbit is elliptical, the distance to Jupiter changes on every orbit. Closer during part of the orbit, further during another part. As that distance changes, the strength of Jupiter's tidal force on the moon changes too. The moon is stretched when it is closer to Jupiter. It is released when it is further away. Then stretched again, released again. On every orbit. That cyclical stretching and releasing generates heat inside the moon. The mechanical energy of being forced into an elliptical orbit. The energy of constantly changing shape slightly in response to changing tidal forces is converted into internal heat through friction. This is called tidal heating. Think of bending a stiff wire back and forth repeatedly. The wire warms at the bend point. The mechanical energy of bending becomes thermal energy. What the Laplace resonance does to Io, Europa and Ganymede is the same process, applied at a planetary scale, sustained by the continuous operation of the resonance over billions of years. The resonance itself is self-reinforcing, which is part of what makes it stable over such long timescales. If one moon drifts slightly out of the perfect resonance ratio, the gravitational interactions between the three moons push it back. The resonance is a kind of gravitational lock that the system falls into and does not easily escape. Once established, it persists, and as long as it persists, the tidal heating it drives also persists. For Io, this has meant billions of years of continuous internal heating with no mechanism available to switch it off. There is no way for Io to lose enough heat to stop the cycle. The resonance keeps the orbit elliptical. The elliptical orbit keeps the tidal force changing. The changing tidal force keeps generating heat. The heat drives the volcanism. And the volcanism continues until something external changes the resonance, which nothing in the current Jupiter system appears poised to do on any human-relevant timescale. The three moons are not sitting quietly in stable orbits around Jupiter. They are being continuously squeezed and released, their interiors heated by the energy of that process, their geological characters shaped by that heating. The heating intensity depends on the distance from Jupiter, because distance determines how strong the tidal force is and how rapidly it changes as the moon moves along its elliptical path. Io, the closest, receives the most intense tidal heating. The consequences are visible from space. Io should look like most moons look. Covered in craters. Grey-brown. Geologically silent. Most solid bodies in the solar system carry the marks of their early history on their surfaces. The heavy bombardment of the early solar system, the period when enormous numbers of leftover planetesimals were still crossing each other's paths and colliding, left deep scars on nearly every solid world. The moon you see at night shows that history clearly. Mercury is covered in it. Even Mars preserves impact craters from billions of years ago. Io does not look like any of those worlds. When the Voyager 1 spacecraft flew past Jupiter in March of 1979 and transmitted images of Io back to Earth, the scientists waiting for those images expected a cratered surface. That is what moons look like. That is what the surface of any world that has been sitting in the solar system for 4 billion years tends to accumulate. What the images showed instead was a world covered in yellows, oranges, whites and blacks. Sulfur and sulfur dioxide in various chemical states, deposited at different temperatures, producing a surface that has been described as resembling a slightly undercooked pizza. No impact craters were visible. Or rather, impact craters existed, but they were being continuously filled and covered by volcanic material so quickly that they did not have time to accumulate before the next layer buried them. Then a Voyager imaging scientist named Linda Morabito was examining a photograph intended to be used for navigational purposes, capturing a star field behind Io for calibration, when she noticed something at the edge of the image. At the curved limb of Io, where the surface met the darkness of space, there was a faint umbrella-shaped structure rising above the horizon. Something was erupting from Io's surface into space. Active volcanism. On a moon. In the outer solar system. It was the first confirmed active volcanism beyond Earth. Io is the most volcanically active body in the solar system, not the most active moon, the most active body anywhere that has been observed. More volcanic activity than Earth. More than Venus, more than any other planet, moon or known object in the solar system. Hundreds of active volcanic centers distribute themselves across Io's surface. Enormous lava lakes cover lowland regions. plumes of sulfur dioxide and silicate material rise hundreds of kilometers above the surface before falling back or escaping into space. The heat that drives all of this is Jupiter's gravity operating through the Laplace resonance. The mechanism is the one already described. Io's orbit is kept elliptical by the resonance. The elliptical orbit means the distance to Jupiter changes on every orbit. The changing distance means the strength of Jupiter's tidal force changes on every orbit. That changing tidal force flexes Io's entire interior repeatedly, squeezing and releasing it like an enormous, slow hand, generating friction, generating heat. Enough heat to melt rock on a world that the sun barely warms, at a distance from the sun where temperatures without that internal heating would be far below freezing. Io's volcanic features are not small. The largest volcanic structure on Io is called Loki Patera, a lava lake roughly 200 kilometers across. Loki Patera periodically brightens as fresh lava resurfaces its dark, solidified crust. A process that has been tracked from Earth by infrared telescopes and observed by spacecraft passing through the Jupiter system. The brightening happens roughly every year or two, though the timing is variable and not entirely predictable. Some of Io's volcanic plumes, the tall ones driven by sulfur dioxide gas pressure, rise so high that their material crosses beyond Io's own gravity and enters Jupiter's magnetosphere. That ejected material, mostly sulfur and sulfur dioxide molecules, is ionized by the radiation environment and begins circulating along Jupiter's magnetic field lines. Io's volcanoes are continuously feeding material into Jupiter's radiation belts, maintaining a torus of ionized sulfur that encircles Jupiter along Io's orbital path. This connection matters. Io's volcanism is caused by Jupiter's tidal forces. The material that volcanism produces enters Jupiter's magnetosphere and strengthens the radiation environment. Jupiter's radiation environment then bombards Io's surface. The relationship between Jupiter and Io is not one-directional, it is a loop. Jupiter heats Io through gravity. Io feeds Jupiter's radiation belts with material. Jupiter's radiation accelerates the chemistry on Io's surface. The same force that creates Io's volcanism also slowly consumes the material that volcanism produces. The variety of Io's volcanic structures is worth pausing on, because it illustrates how completely different this world is from any other solid body we have encountered. Io has shield volcanoes with broad, low profiles built up from fluid lava flows. It has calderas, collapsed volcanic craters, some of which are larger than any caldera on Earth. It has mountains that are not volcanic, but tectonic, immense structures pushed upward by the compression of Io's crust, as it is continuously resurfaced by volcanic material. Io's highest peaks reach over 18 kilometers above the surrounding plains, taller than any mountain on Earth measured from sea level. The surface is not static between eruptions either. The constant deposition of sulfur dioxide frost, which sublimates and redeposits as the sun heats different parts of Io's surface through its orbit, means the visible appearance of Io's surface changes over timescales of years, sometimes dramatically. What looked like one surface feature in Voyager images from 1979 looked different in Galileo images from the late 1990s. Things that were visible are buried. Things that were buried are uncovered. The surface is always moving, always changing. Io is not simply a moon with interesting geology. It is a world caught in a continuous cycle of gravitational destruction and reconstruction, giving material to the planet it orbits, receiving radiation from that same planet, unable to settle or cool or rest. Every surface feature is temporary. Every mountain will be buried. Every lava lake will change. The only constant is Jupiter's grip, and Jupiter's grip does not loosen. The material Io loses to Jupiter's magnetosphere is not negligible on geological timescales. Estimates suggest Io loses on the order of 1 ton of material per second into Jupiter's magnetic field, mostly sulfur dioxide and sulfur plasma. Over geological timescales, this represents an enormous total mass loss. Some scientists have estimated that Io may have lost a significant fraction of its original volatile material over the age of the solar system, stripped away continuously by the combination of volcanic eruption and magnetospheric sweeping. What Io is today, the particular mix of silicates and sulfur compounds visible on its surface, may be a consequence of that continuous stripping, a moon whose more volatile materials have been preferentially removed and whose surface chemistry reflects what remains. Io cannot stop this process. The resonance will not release it. Jupiter will not reduce its mass. The tidal force will not decrease unless the orbit changes, and the orbit is locked. Io is on a path that has been running for 4 billion years and shows no sign of changing. What Io will look like in another 4 billion years, assuming the solar system survives that long and the resonance holds, is a question no one has answered with confidence. But it will have lost more material to Jupiter. And it will still be volcanic. 1 moon further from Jupiter, Europa tells a different story. Not destruction, not scorching volcanism, something quieter. Something that, in its own way, is more unexpected than anything on Io. Europa's surface is ice, bright, white, crossed with a network of brown and reddish streaks and ridges that extend across the surface in long curves and intersecting patterns. The brown material in the streaks is believed to be salt and other compounds brought up from below through cracks in the ice shell. The streaks themselves are where the ice has fractured, separated and refrozen, where the surface has been in motion. There are almost no impact craters on Europa. This is significant, in the same way the absence of craters on Io is significant. A surface with few craters is a young surface. It has been renewed recently enough that the craters from earlier impacts have been erased. Europa's ice surface is geologically young. Something ongoing is resurfacing it. What is doing the resurfacing is the ocean below. The evidence for a liquid water ocean beneath Europa's ice comes not from direct sampling, which has never happened, but from multiple independent physical measurements that all point in the same direction. The Galileo spacecraft, during its years orbiting Jupiter, made repeated close flybys of Europa. One of the things its magnetometer measured during those flybys was the behavior of Europa's local magnetic field in relation to Jupiter's much larger field. What the instrument detected was a response. As Jupiter's magnetic field swept past Europa on each orbit, Europa's own magnetic signature changed in a way that indicated a conducting layer inside the Moon was responding to the external field. This response is called magnetic induction, and its behavior indicates the presence of a conducting material below the surface. The most consistent explanation, the one that fits the data most cleanly, is a layer of salty liquid water. Salt water conducts electricity well. Ice does not. The changing magnetic response detected by Galileo was the ocean beneath Europa's surface responding to Jupiter's external field. Other evidence supports the same conclusion. The pattern of surface features on Europa, the ridges, the chaotic terrain where ice appears to have been disrupted from below, the relative youth of the surface, all suggest that the ice shell is active. That material from below periodically reaches the surface, and that the ice sits atop something that is not solid. By current estimates, the liquid water ocean beneath Europa's surface may be somewhere between 60 and 150 kilometers deep, possibly more. The ice shell above it is estimated to be somewhere between 10 and 30 kilometers thick, though both of these numbers carry significant uncertainty because they are derived from surface observations and gravity measurements rather than direct measurement of the interior. What the estimates are less uncertain about is the total volume of water. Europa's ocean is thought to contain roughly twice the volume of liquid water as all of Earth's oceans combined. Twice Earth's ocean volume in a moon, in the outer solar system, in a place where the sunlight arriving is roughly 27 times weaker than what reaches Earth. The warmth that keeps this ocean from freezing solid is tidal heating, the same force that drives Io's volcanism, but at Europa's distance, the intensity is lower. The tidal force is still real. The orbital resonance still keeps Europa's orbit elliptical, still flexes Europa's interior on every orbit, still generates internal heat. But at this distance, the heating does not reach the scorching intensity that makes Io volcanic. It produces just enough warmth, combined with the heat from Europa's own modest internal radiogenic processes, to prevent the ocean from freezing through. Jupiter's gravity does not apply a single uniform outcome to everything near it. It calibrates by distance. Io, closest in, receives intense tidal heating that produces continuous volcanism. Europa, further out, receives gentler heating that produces an ocean. The physical mechanism is the same. The distance is different. And the distance determines the outcome. The ocean on Europa is not just interesting for its size. The three conditions that scientists currently consider most necessary for life as we understand it are liquid water, an energy source, and chemical complexity. Europa appears to have all three. The ocean is liquid water. Tidal heating provides an energy source. The seafloor below the ocean, where liquid water contacts rock, may provide the chemical environment, including hydrothermal activity similar to what Earth's mid-ocean ridges host, but produces the organic chemistry life has taken advantage of on Earth. Nothing about this confirms life on Europa. That claim has not been made by any serious scientific assessment of the available evidence. What the evidence says is that the conditions we currently associate with the emergence and persistence of life appear to be present, in some form, in a moon orbiting Jupiter. The seafloor of Europa's ocean is a point of particular interest. On Earth, the boundaries between tectonic plates on the ocean floor are home to hydrothermal vents, places where seawater percolates into the crust, is heated by the rock below, and returns carrying dissolved minerals, hydrogen sulfide, and other chemical compounds. Around these vents, communities of organisms exist that are entirely independent of sunlight. They live entirely from chemical energy, not solar energy. These hydrothermal ecosystems were among the first discovered evidence that life on Earth is not exclusively solar-powered. If Europa's rocky seafloor is being warmed from within by tidal heating, similar hydrothermal processes may be occurring there right now. The chemistry would be different. The specific organisms, if any exist, would be different from anything on Earth. But the basic physical setup, warm water meeting cold water above heated seafloor rock, is a plausible analogue. It is not confirmed, but it is physically plausible under the current models, and it is one of the central reasons Europa is considered one of the most significant targets for astrobiological investigation in the solar system. NASA's Europa Clipper mission, launched in 2024 and designed to make dozens of close flybys of Europa over several years, is intended to characterize the Moon's ocean more precisely, assess the thickness of the ice shell, and evaluate whether conditions in the ocean are suitable for life. The mission will not land on Europa or attempt to sample the ocean directly, but it will produce the most detailed assessment of Europa's habitability yet attempted, and the scientific community considers it one of the highest priority targets in the search for potentially habitable environments beyond Earth. That a multi-billion-dollar mission was built and launched specifically to investigate one moon of Jupiter says something about how seriously the scientific community takes the possibility that Europa represents something significant, not confirmed life, but conditions that cannot be dismissed. That ocean should not exist where it does. The Sun cannot maintain it. The Sun barely touches Europa at all, providing less than 4% of the warmth it provides to Earth. Jupiter does what the Sun cannot. And that distinction, a moon kept habitable by gravity rather than by stellar warmth, is something that has no parallel anywhere in the inner solar system. One moon further still, the tidal heating diminishes to the point where it produces neither Io's volcanism nor Europa's ocean in the same form. And what Ganymede has instead is something that no moon was expected to have. Ganymede is the largest moon in the solar system. Not the largest moon of Jupiter specifically. The largest moon of any planet in the solar system, as far as any mission has been able to measure. Ganymede's diameter is roughly 5,268 kilometers. Mercury, the smallest of the 8 planets, has a diameter of roughly 4,879 kilometers. Ganymede is measurably wider than a planet. If Ganymede orbited the Sun directly instead of orbiting Jupiter, planetary scientists would classify it as a planet under any current definition of the term. It orbits Jupiter. Ganymede's surface shows 2 distinct types of terrain that sit side by side across the moon. Large regions of dark, heavily cratered ground, ancient terrain that dates back billions of years, still bearing the scars of the solar system's early bombardment period. And interspersed with those ancient dark regions, broad areas of younger, brighter, grooved terrain, where parallel ridges and valleys extend across the surface in patterns that indicate the ground has been pulled apart and reformed. The grooved terrain is evidence of tectonic activity in Ganymede's past, a time when the interior was active enough to reshape the surface above it. But the most unexpected thing about Ganymede is not its surface geology. Ganymede has its own magnetic field. This is not something that moons are supposed to have. A magnetic field generated internally, as opposed to an induced response to an external field, requires a conducting interior in convective motion, typically a liquid iron or iron-nickel core undergoing circulation driven by internal heat. Earth has such a core, and Earth's rotation of that conducting material generates the magnetic field that compasses respond to. Mars appears to have had such a field in its early history before its core cooled sufficiently that convection stopped and the field disappeared, evidence of which survives in the magnetized rocks of Mars's ancient southern highlands. Ganymede still has one. The evidence came in 2015 when the Hubble Space Telescope was used to observe Ganymede's auroras. Auroras are produced when charged particles, typically electrons and protons from a magnetosphere, enter a magnetic field and spiral along the field lines until they collide with an atmosphere, releasing energy as light. Earth has auroras at high latitudes, produced by particles from the solar wind entering Earth's magnetic field. Jupiter has extraordinary auroras, produced by its own enormous magnetosphere. For Ganymede to have auroras required that it have its own magnetic field to produce them. Observations by Hubble confirmed that Ganymede's auroras rock slightly back and forth in response to Jupiter's magnetic field sweeping past on each orbit. The pattern of this rocking was used to confirm that the auroras are produced by Ganymede's own internally generated field interacting with Jupiter's external field, not simply by Jupiter's field passing through Ganymede directly. The distinction matters because it distinguishes a genuine internal field from a purely induced response. Ganymede also shows evidence of a subsurface ocean in the same magnetic induction measurements that revealed Europa's ocean. The interaction between Ganymede's own magnetic field and Jupiter's external field suggests a conducting layer inside Ganymede, likely a liquid water layer sandwiched between different ice phases at varying depths, rather than sitting directly on a rock seafloor as Europa's ocean likely does. A moon orbiting Jupiter has its own magnetic field, its own auroras produced by that field, and likely its own subsurface ocean. And it is larger than a planet. What the Galilean moon system reveals, taken together, is the range of outcomes that a single gravitational influence can produce. Io, closest to Jupiter, is in continuous volcanic extremity. Europa maintains an ocean that should not exist at this distance from the Sun. Ganymede has a planetary-scale body with its own internal magnetic field. Callisto, the outermost Galilean moon and the one furthest from Jupiter's strongest tidal influence, has an ancient, heavily cratered surface that has changed little in billions of years. The difference between Io and Callisto is not their composition or their formation history. It is distance from Jupiter. That single variable, how close each moon sits to the source of tidal force, has produced 4 completely different geological outcomes from 4 worlds that formed in roughly the same region of the early solar system from broadly similar material. Jupiter's gravity does not only reach inward to its moons, it has been shaping the structure of the broader solar system for as long as it has existed. The asteroid belt, the region between Mars and Jupiter filled with rocky and metallic objects ranging from fine dust particles to Ceres, the largest resident at roughly 940 kilometers in diameter, is often described informally as a failed planet, a place where a planet should have formed but did not. That description is not quite accurate. It implies that planet formation began there and stopped before completion. The more precise account is that Jupiter prevented planet formation from progressing past a certain point. A planet could not form in the asteroid belt because Jupiter would not allow it. In a disk of material orbiting a star, small solid particles collide and stick together, forming pebbles, then rocks, then bodies large enough to have significant gravity of their own. As bodies grow, their gravity attracts more material, and the process accelerates. This is how planets form. It is the process that produced Earth, Mars, and the rest of the rocky inner planets. In the region where the asteroid belt now sits, the same process began in the early solar system. Material collided and accumulated. Bodies grew. But Jupiter, already massive and nearby, kept intervening. At specific distances from Jupiter, the ratio of an orbiting object's period to Jupiter's period creates a whole number relationship. These are called mean motion resonances, or orbital resonances. An object in one of these resonance zones encounters Jupiter's gravitational pull at the same relative position in each orbit, over and over again, with the same timing. The repeated pulls accumulate. The object's orbit is slowly distorted. Eventually the orbit becomes unstable, and the object is ejected from the zone, either toward the inner solar system or outward beyond the belt. These cleared zones in the asteroid belt were identified and catalogued in the 1860s by the American astronomer Daniel Kirkwood. They are called Kirkwood gaps, and they appear as statistically empty regions in the distribution of asteroid orbits when plotted against orbital period. They are not empty because nothing was ever there. They are empty because Jupiter's resonances cleared them over billions of years. The gaps are Jupiter's gravitational signature written into the orbital architecture of the asteroid belt. the asteroid belt today contains much less total mass than models of early solar system formation predict should have been present in that region. Most of the original material is gone. Jupiter ejected it over billions of years, sending objects either crashing into the inner planets or outward to the outer solar system. The Kirkwood gaps are not just historically interesting, they are actively maintained. New material that drifts into a resonance zone from the rest of the belt is still being cleared today. Asteroid fragments produced by collisions within the belt migrate slowly due to a subtle thermal effect called the Yarkovsky effect, in which the absorption and re-emission of sunlight exerts a tiny continuous force on a rotating asteroid, slowly changing its orbit over time. If that slow drift carries an asteroid into a Kirkwood gap, Jupiter's resonance takes over and the asteroid's orbit becomes unstable. It is eventually ejected, either toward the Sun or toward the outer solar system. Some of the asteroids ejected toward the inner solar system become near-Earth asteroids, rocky bodies that cross Earth's orbital path. Jupiter's resonances are, in part, responsible for the population of asteroids whose orbits bring them close to Earth today. Not intentionally, not with any direction. The resonances simply continue doing what they have done since Jupiter formed, clearing objects from certain orbital zones and sending them elsewhere. There is a current model of the early solar system's history called the Grand Tack hypothesis that attempts to explain several puzzling features of the solar system's current architecture, including the depletion of the asteroid belt, the surprisingly small mass of Mars compared to what formation models predict, and the source of Earth's water. The model proposes that Jupiter, early in its history, while the solar system's protoplanetary disk still contained significant gas, migrated inward from its formation location, moving closer to the Sun until it reached approximately the current orbital distance of Mars, before being gravitationally pulled back outward by Saturn, as Saturn grew massive enough to exert its own strong influence on Jupiter's migration. The name Grand Tack comes from the sailing term for a specific maneuver, turning a boat against the wind and then reversing course. The model describes Jupiter doing something analogous at the scale of the solar system, moving in one direction for a period, then reversing and moving outward as Saturn's growing gravitational influence changed the balance of forces acting on Jupiter's migration. The model is not universally accepted. Alternative models for the early solar system's evolution exist, and different teams of planetary scientists assign different levels of confidence to different aspects of the Grand Tack scenario. What is generally agreed is that the solar system's early history was dynamic, that planetary bodies migrated, and that the current orbital architecture, including the sparse asteroid belt and the small size of Mars, requires some explanation beyond the simple picture of planets forming in place and staying there. If this inward and outward migration happened, it would have had enormous consequences for the inner solar system. Jupiter's passage inward would have swept through the early asteroid belt, scattering its material. It may have cleared away a first generation of rocky planets that had already formed inside Jupiter's original orbit. When Jupiter and Saturn reversed course and moved outward, the scattered material included primitive asteroids from the outer belt, bodies rich in water and carbon compounds, which were redistributed toward the inner solar system. Some of that scattered material, in subsequent billions of years, ended up colliding with the early Earth. The water carried by those carbonaceous asteroids is one of the primary candidates for the source of Earth's oceans. The Grand Tack is a model. It is not a proven, directly observed sequence of events. The early solar system did not leave records clear enough to confirm the migration timeline with certainty. But the model is consistent with the asteroid belt's depleted mass, the small mass of Mars, the water content of Earth, and the orbital distribution of different asteroid types throughout the belt, and it is currently one of the leading frameworks for understanding why the inner solar system looks the way it does. If the model is correct, the water in Earth's oceans may be there partly because Jupiter moved. The most widely circulated story about Jupiter's relationship to Earth is a comforting one. Jupiter, the story goes, acts as a gravitational shield. Its enormous gravity catches comets falling in from the outer solar system, the long-period icy bodies that travel on elliptical paths from the far outer solar system toward the inner planets, and deflects them away from Earth's path. Protecting the inner solar system from the kind of relentless bombardment that would otherwise make the development of complex life nearly impossible. This narrative has appeared in popular science writing, in documentary films, in educational materials, and in many accounts that discuss what makes Earth special among the planets. Jupiter is sometimes presented as something like a bodyguard, a large, lucky accident of planetary formation that happened to end up in exactly the right place to absorb or deflect the cosmic debris that would otherwise have prevented life from gaining a foothold on Earth. It is a story with a real scientific basis. Computer simulations of the solar system do, in some configurations, show Jupiter deflecting comets that would otherwise cross the inner solar system. The gravitational deflection is real physics. It happens. Jupiter does redirect comets, and some of those redirected comets are sent outward rather than inward. The problem is that the story, as popularly told, is considerably simpler than the actual dynamics of what Jupiter does to comets. Jupiter's gravity does not only deflect comets away from the inner solar system, it also captures comets from the outer solar system and redirects them inward. A comet travelling on a long elliptical orbit from the outer solar system, one that might never cross Earth's orbital path on its own, can be captured by Jupiter's gravity and placed on a shorter, more Earth-crossing orbit. Jupiter's gravity works in both directions. It can send things away from Earth, but it can also bring things toward Earth that would not otherwise have come close. A study published in 2007 by Jonathan Horner and Barry Jones at the Open University in England ran extensive computer simulations of the solar system with Jupiter at different masses, including the actual mass, a higher mass, a lower mass, and no Jupiter at all. Their results showed that reducing Jupiter's mass sometimes increased the rate of comet impacts on Earth, but removing Jupiter from the solar system entirely in some simulation scenarios also reduced the impact rate, because Jupiter was no longer capturing outer solar system comets and redirecting them inward. An earlier study by George Weatherall, published in 1994, had suggested that removing Jupiter from the solar system would increase Earth's bombardment rate dramatically, because Jupiter currently deflects many of the short-period comets in the inner solar system. The two sets of results are not simply contradictory in an uninformative way. They are showing that the dynamics are genuinely sensitive to the specifics of each individual simulation, to the starting conditions, to the population of comets modelled, and to the time period considered. The honest scientific answer to the question of whether Jupiter's net effect on Earth's comet impact rate has been protective or hazardous is that the question remains genuinely open. Different simulations by different research groups using different methods have produced different answers. What is not in question is the mechanism. Jupiter gravitationally interacts with every comet that passes through its sphere of influence. Some of those interactions send comets away from Earth. Some send comets toward Earth. The planet does not choose. It applies gravity equally to everything, and the result depends on the geometry of each specific encounter. The shield story is not wrong in the sense of describing something that never happens. Jupiter does deflect some comets away from Earth, but it also redirects some comets toward Earth. Whether the net balance of these two effects is positive or negative for Earth's impact rate is not yet determined. What remains true is that Jupiter's influence on comet trajectories is real, ongoing, and continuous. The planet is not a passive presence in the outer solar system. It reaches out gravitationally to everything that comes near it, and it changes the path of what it touches. There is also a distinction worth making between the two populations of comets that might threaten Earth. Long-period comets, the ones that arrive from the distant outer solar system on orbits that take thousands or millions of years to complete, may indeed be deflected more often than redirected inward by Jupiter, since many of their trajectories would not have crossed Earth's orbit anyway. Short-period comets, those with orbits of less than 200 years that regularly cross the inner solar system, may have been placed on their current orbits partly by past interactions with Jupiter that captured them from the outer solar system and shortened their orbits. The distinction matters because the two populations come from different regions and interact with Jupiter's gravity differently. The shield hypothesis may be more applicable to long-period comets, while the hazard hypothesis may be more applicable to short-period ones. The net effect, across both populations and across the full history of the solar system, is what remains genuinely uncertain. Sometimes the change is protective, sometimes it is not. The planet has no preference, and no astronomer studying the question has yet found a single simulation that resolves it cleanly enough to settle the debate. In July of 1993, astronomers Carolyn Shoemaker, Eugene Shoemaker, and David Levy were examining photographic plates taken at the Palomar Observatory when they noticed something unusual in images of Jupiter's vicinity. A comet. But not a single bright nucleus moving through space. Instead, a chain of brightness, multiple individual fragments arranged in a line along a common orbital path, like separate beads strung on an invisible wire stretched across millions of kilometers of space. The comet had already been torn apart. What happened to it was this. Sometime in the preceding decades, likely in the 1960s or 1970s, the comet had passed close enough to Jupiter to be captured by Jupiter's gravity. It was pulled from whatever orbit it had been following around the Sun and placed into an orbit around Jupiter itself. On a subsequent close approach to Jupiter, likely in July of 1992, the comet came within what is called the Roche limit. The Roche limit is the distance from a massive body within which the tidal force of that body becomes stronger than the self-gravity of an approaching smaller object. Inside the Roche limit, Jupiter's gravitational pull on the near side of the comet is measurably stronger than its pull on the far side, and the difference between these two pulls, the tidal force, exceeds the comet's own gravity that was holding its material together. The comet was pulled apart, not by collision, not by an explosion, by the difference in gravitational pull between one side and the other. By the time Carolyn Shoemaker, Eugene Shoemaker and David Levy discovered it in 1993, the comet had already been broken into at least 21 identified fragments, each following a slightly different path strung out over millions of kilometers, all of them in an orbit that would eventually take them directly into Jupiter. The impacts happened over 6 days in July 1994. They were the first extraterrestrial impact event in history to be predicted in advance and observed in real time by the global astronomy community. Telescopes on Earth, the Hubble Space Telescope in orbit, the Galileo spacecraft on its way to Jupiter, and even the distant Voyager 2 from the outer solar system were all directed toward Jupiter for the event. The impacts occurred on Jupiter's night-side hemisphere, just beyond the edge of visibility from Earth. But Jupiter rotates quickly, completing one rotation roughly every 10 hours, and as it turned, the impact sites came into view. What the telescopes showed was not subtle. Dark, circular scars had appeared in Jupiter's cloud tops, each one the result of a fragment entering the atmosphere at roughly 60 kilometers per second and releasing its energy explosively in the upper atmosphere. Some of the impact scars were larger in diameter than Earth. Individual features within the impact sites, the dark material lofted into the upper atmosphere by the explosions, were visible to amateur telescopes. The impact of the fragment designated G, one of the larger pieces of the comet, released energy that scientists estimated to be equivalent to roughly 600 times the combined yield of all nuclear weapons that had existed on Earth at that time. The scar it left was larger than Earth and remained visible for weeks as Jupiter's atmospheric circulation slowly spread and erased the material. 21 fragments entered Jupiter over 6 days. Each impact was a planetary scale event. Jupiter absorbed all of them. A month later, the impact scars were fading. The following year, Jupiter's cloud top showed no trace of Shoemaker-Levy 9. The planet had absorbed a comet that its own gravity had first torn into pieces and had returned to its ordinary behaviour without interruption. The event was not a rare exception. Astronomers believe Jupiter experiences comet and asteroid impacts on a regular basis, though most are too small or occur without warning. Subsequent observations have detected smaller impact events on Jupiter, including a fireball observed in 2009 that left a dark scar, and additional transient flashes detected in following years. Jupiter encounters these objects partly because its gravity attracts them. Shoemaker-Levy 9 was significant not because it was unusual for Jupiter, it was significant because humans were watching. The observation was an extraordinary moment in planetary astronomy. Predictions of where and when each fragment would impact were refined repeatedly in the months leading up to July 1994 as astronomers tracked the fragments and refined the orbital calculations. The comet was discovered just over a year before the impacts, providing enough warning for the global astronomy community to prepare. Professional observatories on every continent that could see Jupiter were positioned and ready. Amateur astronomers set up their equipment. The event was treated as scientifically unprecedented, the first predicted observed collision of two solar system bodies in human history. And then, for 6 days, the impacts happened almost exactly when and where the predictions said they would. The precision of the orbital mechanics behind those predictions was itself a kind of scientific moment. Newton's laws of gravity, Laplace's orbital mathematics, the computing power of the late 20th century applied to the problem, all of it converged to allow astronomers to predict, to within hours and fractions of a degree, exactly where a torn comet would strike a planet hundreds of millions of kilometers away. The planet struck back with marks the size of Earth. What it demonstrated was direct visual confirmation of what the physics had always implied. Jupiter tears apart objects that come close enough. Then it absorbs the pieces. And then it continues as if nothing happened. The entire event, from the first impact to the fading of the last visible scar, covered a span of weeks. For Jupiter, it was ordinary. All of what has been explored in this script, the atmosphere that never calms, the interior where hydrogen is transformed into a conducting fluid, the magnetic field that fills an enormous volume of space with accelerated charged particles, the moons torn by tidal forces into 4 completely different geological outcomes, the asteroid belt interrupted and permanently shaped by orbital resonances, the comets redirected or absorbed, leads back to the question the title of this script has been building toward. Did Jupiter make Earth possible? This question has a more complicated answer than the popular SHIELD story provides, but it also goes deeper than that story. The early solar system was not the stable, organised system that exists today. In the first hundreds of millions of years after the Sun formed, the planets were not sitting quietly in their current orbits. They were interacting with the remaining disk of gas and dust, with the sun's gravity, and with each other. They migrated. They moved. The Grand TAC model proposes that Jupiter's migration was the most consequential of these movements, and that its effects reached all the way into the region where Earth was forming. If Jupiter migrated inward toward the Sun early in its history, its passage through the inner regions of the solar system would have disrupted whatever planetary bodies were already forming there. Some models suggest that a generation of larger rocky planets may have already existed in the inner solar system before Jupiter arrived, bodies that Jupiter's inward migration scattered or pushed toward the Sun. If that is correct, the current inner planets, including Earth, formed in the space left after Jupiter's inward migration and subsequent outward retreat, forming from a different population of material than the first generation. That material included the scattered remnants of the outer asteroid belt, primitive, water-rich, carbonaceous bodies that Jupiter's migration redistributed inward. Some of those bodies impacted the early Earth. Their water contributed to Earth's oceans. Their organic compounds contributed to Earth's chemistry. Earth's water has a hydrogen isotope signature, specifically a ratio of deuterium to ordinary hydrogen, that is consistent with delivery from carbonaceous chondrite asteroids, a class of primitive asteroid from the outer belt. The match is not perfect, and the exact sources of Earth's water remain actively debated, but the carbonaceous asteroid hypothesis has significant support, and if Jupiter's migration scattered those asteroids inward, Jupiter is part of the chain that delivered that water. This is speculative in its specifics, but grounded in real evidence in its broad outlines. The Grand TAC model is not proven, but the evidence that it attempts to explain, the depleted asteroid belt, the small size of Mars, the chemical signature of Earth's water, is real evidence that points towards something large having moved through the inner solar system in the early history of the solar system. If the model is right, Jupiter is part of the reason Earth has oceans, part of the reason Earth has the organic chemistry it has, part of the reason the conditions that allowed life to develop here were present at all. This is a difficult idea to sit with, not because it is uncertain, but because of what it implies about the relationship between the solar system's largest planet and the only world in the solar system we know to be inhabited. The same planet that tears moons apart with tidal forces, that creates a radiation environment hostile to everything alive, that swallowed a comet while the world watched, may also be a critical component of the chain of events that produced the conditions under which life on Earth developed. Neither the destruction nor the creation was aimed. Neither was the result of Jupiter's presence being beneficial or harmful in any intentional sense. They were both the result of mass, gravity, and time, operating in a system that had no preference for outcomes. The late heavy bombardment, a period roughly 3 to 4 billion years ago, during which the inner solar system experienced a significantly elevated rate of large impacts, may also be connected to Jupiter's influence. Models suggest that interactions between Jupiter and Saturn during this period could have destabilized the orbits of objects in the outer asteroid belt and sent a wave of impactors into the inner solar system. If this is correct, the same planet that may have delivered water to Earth also participated in the bombardment that shaped the early geological history of Earth, Mars, the Moon, and Venus. All of this from the same physical source. The same mass, the same gravity, different timescales, different populations of objects, different outcomes. And that conclusion stands alongside every other fact in this script. The same planet whose tidal forces created volcanic Io and oceanic Europa and magnetic Ganymede. The same planet whose radiation belts would kill a human in minutes. The same planet that absorbed Shoemaker-Levy 9. the same planet that shaped the asteroid belt into its current sparse, stirred state. 1. Planet. One set of physical properties. Billions of years. Consequences that include both the creation of potential habitats and the destruction of approaching objects, both the delivery of Earth's water and the absorption of comets, both the active volcanism of one moon and the ocean of another. None of it was aimed. None of it was chosen. All of it followed from Jupiter being massive in the right place at the right time, in a solar system that was still forming. There is one more piece of Jupiter's story that most people have never encountered, a fact that sits quietly at the edge of what is known about the planet. Jupiter has rings, not Saturn's rings. Nothing approaching the brightness, width, or visual drama of Saturn's ring system, but rings. A system of faint, dark structures circling the planet at a distance, invisible from Earth under ordinary observing conditions, unknown to humanity until a spacecraft flew close enough to detect them. Voyager 1 discovered Jupiter's rings in March of 1979. In images taken during its approach to Jupiter, the rings were detected in a specific photograph taken with the Sun behind Jupiter, a geometry that caused the faint ring material to scatter light at an angle that made it briefly visible to the spacecraft's cameras. In that backlit configuration, the rings appeared as thin, faint halos around the planet. In most other viewing geometries, they are too dark and too thin to be seen. Jupiter has 4 distinct ring components. The innermost is a thick, extended region called the halo ring, a broad torus of dust particles filling the space from the inner edge of the main ring down toward Jupiter's upper atmosphere. The main ring is the brightest of the 4 components, a relatively narrow and flat structure extending outward from the halo region. Beyond the main ring, 2 broad, faint sheet-like structures called gossamer rings extend further outward. The inner gossamer ring is associated with the small moon Amalthea. The outer one is associated with the small moon Thebe. Unlike Saturn's rings, which are composed primarily of water ice and range in particle size from tiny grains to objects meters or more across, Jupiter's rings are made mostly of fine dust, not rock, not ice. Dust particles, typically tiny, believed to be mostly silicate material knocked off the surfaces of the small inner moons by micrometeorite impacts. The process works like this. A small meteoroid, a fragment of asteroid or cometary material, impacts the surface of one of Jupiter's small inner moons, Meti, Adrastea, Amalthea, or Thebe. The impact kicks material off the surface. On Earth, that material would fall back to the surface under gravity. But the small inner moons of Jupiter are tiny, with very weak gravity. Ejected material escapes the moon and drifts into orbit around Jupiter, joining the ring system. The rings exist because of the Roche limit dynamics already discussed. Material close enough to Jupiter cannot coalesce into a moon. The tidal forces that tear apart approaching objects also prevent the fine dust in the ring region from clumping into anything larger. The dust circulates in the ring region, slowly spiraling inward under the influence of Jupiter's magnetic field and radiation, and is continuously replenished by fresh material from micrometeorite impacts on the inner moons. Jupiter has had rings for the entirety of its existence, almost certainly. The process that creates them, micrometeorite impacts on inner moons, has been operating for as long as those moons have existed, but the rings were invisible to Earth-based observation for more than 3 centuries of telescopic astronomy after Galileo first looked at Jupiter in 1609. They were not hidden by anything in particular. They were simply too faint and too dark to be detected from Earth, with the technology available until spacecraft could visit. The contrast with Saturn is instructive. Saturn's rings are made of water ice which reflects sunlight efficiently. They are visible from Earth even in modest telescopes. They were recognized as rings by Christian Huygens in 1659, less than half a century after Galileo's first telescope observations of the solar system. Saturn's rings announce themselves through their brightness. Jupiter's rings are dark. They are made of dust rather than ice. They reflect very little sunlight and absorb the rest. They are only visible in specific geometries, primarily when sunlight passes through or behind them and scatters forward to an observer looking back toward the Sun. That geometry, with the observer on the far side of Jupiter from the Sun looking back through the ring material, is not a geometry that Earth-based observers can access. Earth is always roughly in the same direction as the Sun from Jupiter's perspective. The geometry that reveals Jupiter's rings requires a spacecraft that has flown through the Jupiter system and is looking back. The rings were always there. The entire time that humanity was observing Jupiter, categorizing it, naming its moons, measuring its atmospheric features, sending missions to photograph it. The rings were circling the planet invisibly. That is a quiet version of this script's central argument. The image of Jupiter that humanity carried for centuries was always incomplete. What the planet was doing, what it contained, what it was made of, were all hidden behind a veil of distance. The completeness was never there. Only the limits of observation made it seem complete. So what does terrifying mean when applied to a planet? It does not mean dangerous in the immediate personal sense. Jupiter is not approaching Earth. Its orbit is stable. It is not sending its radiation directly at Earth's surface. Nothing about Jupiter's current behavior poses a threat to anything living here. That is not what the word means in this context. Jupiter is terrifying in a more specific and more accurate sense. It is the most consequential object in the solar system after the Sun, and it has been reshaping that solar system without knowledge, without intention, and without any mechanism for distinguishing between outcomes for billions of years. It operates at a scale where human concepts of protection, threat, purpose, and choice simply do not apply. Io is volcanic because Io happens to sit at the distance from Jupiter where tidal heating reaches the intensity required to melt rock continuously. Io did not earn that condition. It did not choose it. Physics produced that result from the geometry of the resonance and the distance. Europa has an ocean because Europa sits far enough from Jupiter that tidal heating is gentler. The same mechanism that turned Io into the most volcanically active body in the solar system kept Europa just warm enough to maintain liquid water. Physics produced both outcomes from the same input, only the distance changed. Jupiter may have migrated inward in the early solar system and scattered the outer asteroid belt material, some of which eventually reached the early Earth and delivered water. Not because Earth was the target. Because Jupiter was massive and the disk was present and migration was a natural outcome of those conditions. Jupiter absorbed Shoemaker-Levy 9. Not because it was defending anything, because the comet came within the Roche limit and tidal forces did what tidal forces do when the differential is strong enough. Jupiter's radiation belts would kill a human in minutes, not as a defense mechanism. Because the magnetic field is strong enough to trap and accelerate particles to those energies, and that is what strong magnetic fields do when charged particles are present. There is a tendency, when confronted with facts like these, to reach for language that implies direction. That Jupiter is attacking something, or guarding something, or threatening something. The language of intent creeps in because we understand the world through agency. We look at an outcome, and we look for what caused it, and we attribute to the cause some version of purpose. Jupiter has no purpose. It has mass. It has gravity. It has a rotation that drives its magnetic field. It has a position in the solar system that has been mathematically determined by 4.5 billion years of orbital dynamics. None of these things are for or against anything. They simply are, and the outcomes they produce in the surrounding space depend entirely on what is nearby. This is not a soft philosophical point. It is the precise thing that makes Jupiter unsettling. A genuinely dangerous entity, something with intention, can be reasoned with, appealed to, avoided strategically, negotiated around. Jupiter cannot be reasoned with. It does not notice anything you do. If a comet happens to cross its gravitational field at the wrong angle, the comet's path changes. If a moon happens to orbit at a resonance distance, that moon's interior is heated. If a spacecraft enters the wrong region of the radiation belts, its electronics are damaged. The outcomes are not punishments, they are physics. The terrifying quality of Jupiter is not any single one of these facts. It is the combination of all of them under a single physical explanation. Jupiter is massive. Mass has consequences. And at the scale of the solar system, over the timescale of billions of years, those consequences reach into the structure of the asteroid belt, the geological character of 4 major moons, the orbital paths of comets, and possibly the chemical composition of Earth's oceans. Jupiter produced all of these outcomes. It does not know any of them happened. That indifference, paired with that scale of consequence, is the most accurate definition of terrifying that applies here. Go outside on a clear night and find Jupiter. If it is above the horizon, you will not have trouble identifying it. It is one of the brightest objects in the night sky, a steady, slightly yellowish point that does not flicker the way stars do. It has been in human skies for all of recorded history, watched by every civilization that looked upward, named after gods, tracked by astronomers, eventually reached by spacecraft, and still, from this distance, it looks like a point. The light you see left Jupiter somewhere between roughly 35 minutes and over an hour ago, depending on where the 2 planets are in their orbits. It has travelled several 100 million kilometres through empty space to reach your eye. When it left Jupiter, it reflected off cloud tops above an atmosphere where wind patterns have been running continuously for billions of years, where the Great Red Spot has been rotating for longer than any human institution has existed, where the boundary zones between competing jet streams churn in patterns that look almost alive in high-resolution images from spacecraft that have made the crossing. Below those clouds, no surface weights. Only increasing pressure and temperature, a slow transition from gas to something denser, eventually into a state where hydrogen itself loses its ordinary behaviour and becomes a conducting fluid. That fluid is spinning with the planet right now, generating the magnetic field that extends outward far enough that if it were visible, it would appear larger than the full moon from where you are standing. Around that point of light, invisible to you from here, Io is being worked from the inside by Jupiter's tidal force, its surface continuously covered and recovered by fresh volcanic material. Europa is carrying an ocean larger than any ocean on Earth, hidden under ice, kept liquid by the same force that makes Io volcanic, kept stable in the darkness where the sun provides almost no warmth. Ganymede is orbiting with its own magnetic field, producing auroras that could be seen from close range as curtains of light responding to Jupiter's external field. Callisto is turning slowly, its ancient surface unchanged, a record of what these worlds were before Jupiter's reach fully asserted itself. And somewhere in the space around all of that, in the radiation belts that Jupiter's field has filled with accelerated charged particles, the environment is such that anything unshielded would not survive long. All of this is what that point of light represents. The planet has not changed since you came outside. It is the same object Galileo watched in 1609 when he noticed the 4 small lights near it changing position from night to night. It is the same object that the Voyager spacecraft photographed in 1979, revealing the great red spot in startling clarity and discovering the volcanic plumes on Io and the rings that no one had known were there. It is the same object the Galileo probe fell into in 1995, transmitting data for 57 minutes before the planet absorbed it. The same object Juno is still orbiting today, its titanium vault protecting its electronics as it makes close polar passes through the radiation environment near the planet. The same object that spacecraft like Europa Clipper and the JUICE mission are travelling toward right now, crossing hundreds of millions of kilometres to take a closer look at what the centuries of Earth-based observation could not fully resolve. All of those spacecraft, all of that engineering, all of that time and calculation are aimed at understanding more completely what that single point of light represents. And they are each discovering more than was known before, which is itself a pattern that has repeated every time a new instrument or spacecraft has looked at Jupiter more closely than the last. Galileo's telescope revealed moons. Voyager revealed volcanic Io and Europa's strange surface. Cassini added detail on its flyby. Galileo the spacecraft revealed the magnetic evidence for Europa's ocean and the atmospheric data from the probe. Juno revealed the depth of the jet streams and new detail on the great red spot's routes below the clouds. Each improvement in observation revealed more complexity than was visible before. The image you see from here has always been incomplete. The point of light has always been in front of something far larger than what it appeared to be. And every time humanity has looked more closely, more has been there. That is not a failing of the eye or the mind. Distance does what distance does. It simplifies, it reduces, it lets you look at something this consequential and feel, briefly, that you understand what you are looking at. But now, having come this far through what Jupiter actually is, what its interior produces, what its gravity does to everything near it, what its presence has meant for the shape of the solar system over billions of years, the point of light is not quite the same as it was before. You are still looking at it from the same distance. The planet has not come closer. The image has not changed. The light still takes the same amount of time to arrive. The planet is still moving in its orbit, 12 Earth years to complete one circuit of the Sun, so slow that it seems to barely drift across the background of stars from week to week. It has been doing this circuit continuously for 4.5 billion years. Before Earth had oceans, before Earth had an atmosphere, before any living thing had ever converted sunlight into growth. Jupiter was already there, already orbiting, already massive, already shaping the space around it. What has changed is what you know is behind it. Jupiter is not terrifying because of any one storm, any one moon, any one radiation belt, any one absorbed comet. It is terrifying because it is the solar system's most consequential object after the Sun, because its influence is woven into the structure of everything near it, because that influence has produced both destruction and oceans and volcanic fire and the water you carry in your body, and because it has done all of this without awareness, without intent, and without interruption, for longer than anything living has existed on the planet you are standing on. The point of light is still there. Look at it a little longer. The light left Jupiter some time ago. It crossed all that empty space. It reached your eye, and for the duration of that crossing, Jupiter continued doing what it always does, rotating, generating its magnetic field, heating its inner moons, shaping the belt beyond Mars, turning in an orbit it has followed for longer than any living thing on Earth has existed. The light is still coming. Good night.